In this video, we're going to continue our discussion of Taylor and Maclaurin series. The question here is to find the sum of the series summation n equals 0 to infinity minus 1 to the power of n times x to the power of 2n divided by n factorial as a function of x. Let's start with the Maclaurin series of e to the x. E to the x is equal to summation n equals 0 to infinity x to the power of n divided by n factorial, with the interval of convergence x less than infinity larger than minus infinity. That means this series converges for all values of x. Now let's rewrite the question that we're given, summation n equals 0 to infinity, in a different way such that we can fit it into the pattern of e to the x. So we have minus 1 to the n times x to the power of 2n divided by n factorial. We can rewrite this as summation n equals 0 to infinity minus x squared to the power of n divided by n factorial. This suggests that we should replace x by minus x squared in the Maclaurin series for e to the x. Replace x by minus x squared. All right, so we have e to the x is equal to summation n equals 0 to infinity x to the power of n divided by n factorial. Let's replace x by minus x squared. So doing that, we get e to the minus x squared is equal to, so wherever you see an x, replace it by minus x squared. We get summation n equals 0 to infinity minus x squared to the power of n divided by n factorial. So in fact, the sum of the series that we were given, this is the series that we were given. The sum of this is e to the minus x squared. Let's summarize. So we're given summation n equals 0 to infinity minus 1 to the power of n x to the power of 2n divided by n factorial. We did some algebra and we rewrote it as n equals 0 to infinity summation n equals 0 to infinity minus x squared to the power of n divided by n factorial. Then we realize that this Maclaurin series is nothing but the Maclaurin series of e to the x. Well, actually, it's e to the minus x squared because this is our new x. So the sum of this Maclaurin series is e to the minus x squared. So the replacement of x with minus x squared is permitted because minus x squared is inside the interval of convergence of the series for e to the x. That is, minus x squared is less than or equal to 0, larger or equal to minus infinity, and of course less than infinity, because 0 is less than infinity. So minus x squared is between minus infinity and infinity. All right, let's look at another question. Find the sum of the series given by recognizing it as a Taylor series evaluated at a particular value of x. So we're given 2 plus 2 squared divided by 2 factorial plus 2 cubed divided by 3 factorial plus 2 to the 4th divided by 4 factorial and so on. And a general term is 2 to the power of n divided by n factorial. Now, if we look at this closely, we realize that this series almost fits the pattern of the Maclaurin series for e to the x evaluated at x equals 2. So let's look at the Maclaurin series for e to the x. E to the x is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus and so on. And the general term is x to the power of n divided by n factorial. Now plug x equals 2. So plugging x equals 2, we will get e to the power of 2 is equal to 1 plus 2 plus 2 squared divided by 2 factorial plus 2 cubed divided by 3 factorial and so on. And the general term is 2 to the power of n divided by n factorial. So this is key. When you plug in x equals 2, anywhere you see an x, you should plug in x equals 2. So plug it here, plug it here, plug it here, and into the general term. Now, the question was asking for the sum of this part of the series. 2 plus 2 squared divided by 2 factorial plus 2 cubed divided by 3 factorial, and so on. So what we should do is subtract 1 from both sides to find the sum of the given series. So doing that, we get e squared minus 1 is equal to 2 plus 2 squared divided by 2 factorial plus 2 cubed divided by 3 factorial plus and so on. And the general term is 2 to the n divided by n factorial. And this is an infinite series, so we should actually put dots after that as well. So now we have found the sum of this infinite series, and the sum of this infinite series is e squared minus 1. So the key concept is to try to fit the pattern of a given series with one of the known Maclaurin series, such as e to the x, sine x, cos x, tan minus 1x, because these are some of the most common Maclaurin series. So let's actually look at some of the common Maclaurin series that you'll be using in a general integral calculus course. So the first one is a geometric series that we may have looked at earlier, 1 over 1 minus x. This is a sum of a geometric series with a common ratio of x. And the Maclaurin series expansion of that is 1 plus x squared plus x cubed, and so on. We can write it in a compact way, summation n equals 0 to infinity, x to the power of n, and this is the interval of convergence for this geometric series. These are all the values of x for which this series converges to 1 over 1 minus x. And e to the x is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial. In compact notation, we can write it as summation n equals 0 to infinity, x to the power of n divided by n factorial. And the interval of convergence is all values of x large than minus infinity and less than infinity. And sine x is very easy to memorize because sine x is an odd function, and the Maclaurin series involves only odd powers of x minus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial, and so on. So of course we always need a negative 1 to the n. This is what generates the plus and minus, and to generate the odd powers of x, we write the x as x to the power of 2n plus 1 because that generates odd powers of x. And the interval of convergence of sine x is all values of x from minus infinity to infinity. Now, to find the Maclaurin series of cosine x, you can simply differentiate the Maclaurin series of sine x, or you can just memorize it or look it up in a table. And cosine x is an even function, so just like before when sine x was an odd function, the Maclaurin series only involved odd powers of x. So for cosine x, the Maclaurin series only involves even powers of x squared, x to the 4th, x to the 6th, and so on. And the general pattern is summation n equals 0 to infinity, negative 1 to the power of n times x to the power of 2n divided by 2n factorial, and x to the power of 2n generates even powers of x. And also we have the Maclaurin series of arctangent of x, tan minus 1x. This is very similar to the Maclaurin series for sine x, except you don't have the factorial in the denominator. So it's easy to memorize. It's just like sine x without the factorial. So we get x minus x cubed divided by 3 plus x to the 5 divided by 5, and so on. And in compact notation, we get summation n equals 0 to infinity minus 1 to the power of n. This part generates the plus and minus, and x to the power of 2n plus 1. This generates the odd powers of x divided by 2n plus 1, and the interval of convergence is between negative 1 and 1. The radius of convergence for arctangent of x would be r equals 1. All right, thanks.